we're going to start our problem with the trapezium. Then, on the right leg of the trapezium, we're going to put a point which is going to divide this leg into two identical segments. Now we will connect this point to the bottom left and the top left corners of our trapezium. And in this way we will divide our trapezium into three triangles. Let's say that the bottom triangle has the area of 3 and the top triangle has the area of 2. The question is, can we somehow calculate the area of the middle triangle? Now, as always, you guys can pause the video right now if you want to try this one out for yourself and then come back and check the solution. Alright, so let's solve this problem. So, this problem can actually be solved in just a couple of seconds by using a really awesome trick. And a lot of mathematicians know how to do this. And I'm going to show you first, and then I'm going to explain to you how we can do that. And then I'm going to explain to you in a great detail how we manage this. So the solution is quite simple. If the point is located exactly in the middle of the leg of the trapezium, then the area of the middle triangle is nothing but the sum of the areas of the other two triangles, so the area of the middle triangle is 2 plus 3, which equals 5. And as you can see, you don't need more than a couple of seconds to do this. So now you're probably wondering, how is this possible? And you're probably wondering if this applies to any trapezium and any case. And the actual answer is yes. The only condition is that the point is exactly at the middle of the leg of the trapezium. So how do mathematicians know about this and what's the catch? Let me explain. So, first we're going to construct a parallelogram using our trapezium. And the question is how? Well, we're going to use our middle point. First, we will pull a line through this middle point, which is parallel to the other leg of our trapezium, and we're going to pull another line which is parallel to the bottom base of our trapezium. And therefore, we will construct this really nice parallelogram. Now, this is important because this parallelogram and trapezium have constructed two triangles which we need. The bottom right triangle on the sketch and the top right triangle on the sketch. And these two triangles are super important. So, for the sakes of better understanding, let's label them as A, B, C, D, and let's label their common point as O. Now, let's have a look at those two triangles. First, we're going to use a couple of things to show that those two triangles are congruent. We're going to use the angles formed by intersecting lines first. The angles formed by intersecting lines are always identical. And in our case, the lines DB and AC are intersecting lines, so this means that the angles at the point O for both of those triangles are identical. Alright, so now let's use another theorem, which is called the angles in parallel lines. So if we have two parallel lines and we pull a line through them, which is actually called a transversal, then the alternate angles are identical. As you can see, we have the same situation on our sketch. Since the lines DC and AB are parallel, and the line DB is actually a transversal, this means that the alternate angles, or the angles at the point B and the point D, are actually identical for those triangles. Alright, so now let's just write down what we have. We have that the both angles at the point O are identical for both triangles, and the angle at the point D is identical to the angle at the point B. But we also know that the line DO is equal to the line OB, since the point O is the midpoint of the line DB from the condition of our problem. So now, using those three facts, we know that these two triangles share two of the same angles and the side in between those two angles. So, by the angle-side angle theorem, we have proven that those two triangles are, in fact, congruent. Alright, so now let's clear our sketch a little bit, and let's label the other two vertices of our parallelogram as P and Q. Now, remember, from the start of our problem, we know that the triangle PBO has the area of 3, right? And let's take a look at the triangle ABO. And let's say that this triangle has the area of x. Now, if we take this triangle out of our triangle PBO, the remaining blue triangle PAO will have the area of 3 minus x. Alright, now take a look at the triangle DQO. This triangle has the area of 2 from the start of our problem. And since we know that the triangles ABO and CDO are congruent, we can rotate the triangle AOB on the top. And in this way, we have formed this new triangle QCO, who has the area of 2 plus x. Alright, so now in order to solve our problem, we only need to pull a line through point O, which is parallel to the base of our trapezium or our parallelogram. And let's say that the intersection point between this line and the line PQ is M. Alright, so now finally we just need to know a property of parallelogram, that if we have a parallelogram and we pull a diagonal of the parallelogram, the diagonal will always divide the parallelogram into two triangles with identical areas. Why is this important? Well, if you take a look at our sketch on the left, you can notice the small parallelogram on the top, MOCQ. And you can notice that the line OQ is nothing but the diagonal of this parallelogram. This means that it will divide it into two identical areas, so this means that the red triangle MOQ must have the area of 2 plus x as well. Now we can repeat the same logic for the bottom parallelogram PAOM. We can see that the line PO represents the diagonal of this parallelogram, which means that the triangle PMO has the same area of 3 minus x as the triangle PAO. Alright, so now let's clear all this stuff and let's go back to the original image, and as you can see, now you can easily find the red area as the sum of the areas of 2 plus x and 3 minus x. Of course, we can cancel out plus and minus x, and we will get that the area is 2 plus 3, which means that the red area equals 5, and that's our answer. And as you can see, this applies to any trapezium which has the same starting conditions. So, I hope you guys enjoyed this problem. If you did, do not hesitate to leave a like or subscribe to the channel for more problems like this in the future. And if you knew about this trick and you could calculate this in just a few seconds, please write it down in the comment section. I really like to know how many of you actually know about this trick. Alright, and until next time, as always, see you guys and take care.